Welcome to our webinar on the optimization module for multiphysics for IronCAD. I'm Kerry O'Connor and I'll be with you today for this presentation. So multiphysics for IronCAD is an add-on to IronCAD that offers many FEA capabilities including stress, thermal, fluid flow, electrical, fatigue, rigid body kinematics, and now optimization. So let's hop into this presentation to explain a little bit more about what the optimization module is. Okay, so what is the optimization module? So to put it in a nutshell, the optimization module takes your CAD design and its parameters and drives those parameters to meet specific targets such as displacement magnitude and runs analysis operations adjusting those parameters to get to that optimized target, whether you're looking for a minimized result or a maximized result in those targets for displacement or stress or strain or other variables that you want to look for. This is all completely integrated into the multiphysics for IronCAD product. It allows the user to set the parameters, their values, such as the initial, the maximum, and what your starting values are for each parameter that you're looking to drive, and simply run the optimization. The optimization will go through multiple iterations up to your maximum set iteration, and will converge to the solution based on the tolerance that you're giving it. So this is very convenient for analysis users, especially design users, to really test their design, build their products, adjust the parameters, see which design parameter will actually meet these specifications so they can continue to design in the right direction. So in this demonstration, we'll cover these areas and give you an example of how this works in IronCAD in the multiphysics for IronCAD product so that you can make use of this in your own designs. This capability is offered in IronCAD 2025 Service Pack 1, and you can download the latest version of MPIC from our website at this location, ironcad.com/MPIC, which will continue to update to new improvements to this optimization module or other MPIC improvements. Again, this is an add-on product to the Multiphysics for IronCAD Basic or Advanced modules that you purchase as the starting point for your analysis needs, and then you can add optimization to those modules. So let's go ahead and hop into the demonstration and we'll talk about how this actually works. For this demonstration, we'll cover two things. One, we'll set up how to actually use the optimization module from start to finish with a simple example, basically starting the FEA application, adding your various constraints, loads, and running your analysis, then setting up the optimization, and just to give you an idea of how the whole process works. And then we'll go into our example model here, which is this platform model, and we'll change the parameters for our brace to optimize the minimum magnitude, displacement magnitude on this platform. So let's go ahead and hop into IronCAD and let's get started. Okay, so first we're going to start off with a simple shelf model, and what we've got here is basically we're going to have a wall that's sitting back in the back, and we have some height requirements and width requirements of this wall, and we also have the shelf that we're designing. It has an overall length. What we want to know is if we put a load on our top of our shelf, what will be the displacement and the stress on that shelf? And then what if we change the parameters of our angle brace support? How will that change? So that's where our optimization will come in. So we can actually drive the placement of this. So I'll give you an idea. So if we go into our parameters here, and I'll open this over here to our screen so we can see this. And on our shelf, we have some parameters that define the angle length inside of here. So that's kind of this top length here. And we have the depth, which is the vertical direction. And then we have the width of this, so the width of this platform here, we can adjust the width of our brace and also what the thickness of that is. So we have multiple variables that we want to drive, and we notice that these are our driving parameters that's in IronCAD, and below that, if we look at all those parameters, we can see that there's other parameters that are being driven by expressions, whether it's just pulling these values or doing some mathematical functions. Inside of here, these are the expression ones, and you'll notice when we use the optimization, these won't be loaded into the optimization, only the ones that are at the top level or throughout the model that are available to set values to them will be loaded, which is a nice handy feature to have. So let's go ahead and start with this and how do we use multiphysics. So multiphysics is found in our add-in ribbon bar, and you'll see the IronCAD multiphysics setting right here. And you simply start off by selecting Add FEA. And again, we have various types of analysis that you can select, which is static, steady state analysis, dynamic, transient, buckling. You can select those type of things, but for our case, we're just going to go ahead and go into the static analysis here, and you'll see our browser that will appear on the right hand side allows you to go through step by step to get the model prepared for analysis. So first thing to do is selecting your analysis types, and we're just going to look on the stress in this case. Again, we have other types that you can enable here and get those variables in your results as well for like thermal, fluid, electrical. All those are available to you if you have those licenses for those particular add-ons. But what we want to do is we're going to use the stress, and then we're going to go into our next step, which is setting up the model details. So in our case, we have material set for this part, and we're just going to use the same material for both of these. And it gives you a material list here that you can select through. In our case, maybe we'll just select a aluminum case here and just set that. So it really matters in this example, just showing you can set the material for those, and you can do it per body or all the bodies at once. It's up to you. Next, we want to go ahead and add a constraint to this. So what is your fixed constraint? For example, in our case, we want to lock the position down for our wall, and we'll just use this back face here, so we can just rotate around, select our back face, and we've got that face now fixed, and hit OK to apply that. And you can see a little icon showing you that that's a fixed location in space. Next, we want to go ahead and add our loads to this. So we're just going to go step by step all the way down the tree until we get everything ready. So what we're going to do is just add a load or a force onto our top face, and we can select directions. For example, we're going to set the component direction to be Z in this case, and we want it to go the opposite direction. So we're just going to reverse that, and you can see the arrows showing us which way it's going, and we can apply the value to this. So we're going to go ahead and hit OK to use those defaults. Now we're pretty much set up for this. We can go into the next step is the meshing. So at this point, you can simply run AutoSolve and go through and mesh and AutoSolve it with all the defaults, or you can go and customize this if you like. So for example, in mesh generation, you can go in here and adjust how coarse you want it or how fine you want it. If you want some refinement on the curvature, if you have blends, for example, things like that, how you want those to be refined. It doesn't really matter much in this model. It's going to go pretty quick. So we'll just leave those settings on. And you have advanced settings as well. So we have two types of unions on here for the meshing. So you can use a discrete facet union, which is really powerful, that it can handle a lot of your CAD errors that might be existing into large assemblies where you might have some slight interferences or gaps inside the model. That faceting with the using the facet union can handle those cases, and you can give tolerances and inside of there to handle those cases a lot faster in those particular use models or those particular cases you get with those assemblies. But you can also use the CAD precise model here if everything's precisely aligned, no interferences, no gaps inside of there. This can be unioned and using basically IronCAD's kernels, the ACES or Parasol kernel, to give you the results in a precise fashion, and usually is pretty much faster than the facet-based process, because this does have to account for the tolerances and things like that it's working with. So that's just some information that you can use, but you can use either one of those for this case. It doesn't really matter. So what we're going to do is go ahead and hit select generate, and this will go through and mesh this, and you'll see the mesh here, and you can see that this union these two together, these are two different parts, but you can see the mesh at a continuous point at all these points here that is going through and tell you that it's fully glued together. So this is really nice about the multi-physics for IronCAD. It glues everything together automatically for you using that the meshing capabilities that we have, which is some unique capabilities in this product. But you can also add defined glued groups if you need to, like you can glue certain groups together. If there's gaps inside of them, you can actually glue those together to help them transition between the two parts. So that's just some information that you can do there. Next, you simply just want to run the results, so you can hit auto solve and go into the solving. This is our solving window here, and these dialogues can be moved around if you like, but anyways, the result will come back here and show you in this case. We're looking at the displacement magnitude inside of here. We can see where the displacement's happening on this based on that load, and if you run an animated scale, it gives you kind of exaggerated results, but you can see that displacement occurring here on this model. We can also change the contour. For example, if we want to look at the stress on this as well, we can change it down here to the stress, update our screen, and we can see where the stress loads are on that as well during that animation. So you can see high points here in the center, down here at the bottom. If we look underneath here, there's some high points here as well on this model. So we can kind of get an idea of what we've got as a starting point with our current parameter values. Now, if we were to wanted to do this manually, so what we've just done here is just run this auto solve. If we wanted to change our parameters manually, we could go back to the model, go into parameters inside of here, change these top level parameter values for our shelf. We can change those values, hit OK, and hit sync and auto solve, and keep doing that and getting the results and seeing which one works, taking notes and doing that. But this is where the optimization comes in. So we don't really want to do that manually. We wanted the system to find it for us. So this is a fairly quick model. That's why I'm using this design. So what we want to do is run the design optimization on this. And you'll find this down at the bottom of your results dialog. So I kind of went quick there, but you want to click on the results, and you'll see design optimization once it's enabled. and you'll have this dialog here, which gives you all the parameters that you need to set up the optimization. Again, we have multiple optimization methods inside of here. We use this direct global response optimization as the default. But you can select other types as well. But this is the best one for basically a CAD user based optimization. So, that's not an advanced user of analysis. This would be the best one to use, but you can use these to refine, or if you have other issues with the results, you can refine that using those other settings. And if you want to know more details about anything in MPIC, if you select on any node inside of here or any dialog and hit F1, it'll load the help system and it'll take you right to whatever you have selected, in our case, the design optimization, and it'll give you more details about the application. So you can read more about the capabilities inside of here and also all these optimization methods that's called out here, and gives you a little bit more descriptive information about how each of these work inside of there. And also gives you information about all the options inside of this dialog. You can just kind of scroll through this to read more details if you like. And so you can see how we're going to go ahead and do this. We'll just go through the process. So by default, what we're doing is a design optimization, and notice these are the parameters that I mentioned earlier on, the length, depth, width, and thickness that automatically got pulled inside of the optimization dialog. Now, it didn't pull any of the other ones in, as I mentioned before. Since those were being driven by parameters, those are neglected and don't come into the system, which is nice, so I don't have to deal with a whole lot of parameters. But if you did, you can simply disable all and just enable whichever one you want. So if you want to enable just one or two, you can enable those, and these are your working set. These are the ones that are not being worked on, but you can also enable them all. So it's a very nice feature to move these parameters around for what you're trying to work with. Next, you want to know is how many iterations that you want to use in this case. We're going to set it up to 30 step iterations as the maximum that it needs to go to. You can, by default, it usually sets it up for 30. You can adjust that lower or higher depending on what your needs are. And this convergence tolerance is basically a percentage of the process of your model on how to get to a converging result for your optimized target. So usually this is a good level here to start off with, but you can adjust that as well. Next, you want to set your initial and your maximum value for each parameter. So in our case, I'm just going to move this over. Can we kind of see this here? So our length again is from here to out here. That's what our value was for that. So what we want to do is set what's the initial value is. It doesn't really matter much. You can use that as the starting point, but you can adjust that to start at a smaller one, work its way up, or set it halfway, however you like. It's up to you. But what we want to do is set the minimum value. We'll say for the top edge, we want it to only go in maybe minimum distance from here is 2 inches, and the maximum on there is about 7. So let's go ahead and set that to 6 for the maximum length. The depth inside of here, again, we can set the minimum. We'll say maybe 1.5, and the maximum on that value is this whole total distance was 5 something in there. So we'll set that to about 5 as well. So we'll set those two main drivers for that. And then our width, again, the maximum width of this thing can be 5. And set there maybe our initial value, we'll set it to 2. And the minimum, we'll set it to, let's just say the minimum is 1 for that. So we're just going to set some ranges that we want for our design. And our thickness inside of here, again, we know what our initial value is, our maximum value. We can say that we don't want to go bigger than a 0.25. We'll start at 0.125 as our minimum value there as well. So now we've got those set. We're good to go. So next is really what we are looking to optimize towards, so our target. So in our case, we're looking for displacement magnitude, and that comes up by default for the system, especially for the stress cases. That will be your default inside of there. But you can add other ones. So for example, if you wanted to add the stress, which we mentioned as well, we can select stress and say add that as well. So we can look at both of these targets that we want to look for. So we want to minimize each one of these, or you maximize it if you like by changing the types over here, but we're going to want to minimize both of these. And we can also set what the weight is. So which one's the highest priority? Is it this displacement that we want to concern ourselves with, or the stress in this case? We can set them to level 1 and set the other one to level 2. So for example, maybe you want to split the displacement magnitude as 2. That would be the second one, but it'll try to solve both of those minimized cases, but this is the priorities or stress inside of here, and we can just tab out of that dialog or save these settings to save this. So once we go ahead and hit save all settings inside of here, you can see that it's all saved. If you close it, and if you return back to there, all your values that you set, for example, the 30 and all these things are all set inside of here for you to begin your analysis. So that's always good, useful to save your settings inside of there once you set those. Now that everything's set in this dialog, all you do is simply hit run optimization. So this is where the application does all the work for you. It'll essentially run through all those parameter values and adjusting them between those ranges of the initial and the max values using between the minimum value and the maximum value, and using your initial values to start off with. So you can see the model here. I got the dialog set up this way so you can see the model change, which is very nice. You can see if you had parameters incorrect or too big, too small, they may cause them to fly off or come off the part or something like that, for example. But you can kind of see how the model is reacting, what the stress is doing, so you can kind of see those. In this case, it's pretty quick, but you can kind of get an idea of what's happening, and these variables are being changed. And if you look at the dialog, you also see this red area here. So this is actually going through the iterations, which you can see up here where it says iteration number 11. We're on number 11. It's changing those values and trying to get down to that convergence of a optimized result between all those parameters. So this will continue to run until it gets to an optimization based in that range, or that tolerance range that we set. So let's go for a little bit longer here. And what it'll do is it'll come back and tell us what the optimized parameters are for this particular model to meet those two targets that we set. So you can see that it's getting close to converging here, so probably another one or two results here. And you can also notice how quick this is happening inside of here. So we'll get to this a little bit later, but we do use multiple processors on your computer, and it runs very fast, and it uses our technology, the CFA technology, to make this process very quick. So in this model, it comes back at the end. It says basically these are the optimized parameter results for each one of your parameters that you set to meet your specified targets. And it did this in basically went through 22 iterations, and it became number 19 is the optimized result inside of there. So we can get that information, and when you set OK, you can write this information down, but if you hit OK, it'll ask you, do you want to set those if it's not currently set? We can say yes. We can see our model update inside of here, and then we can, if we'd like to keep this dialog open so we can look at it, but what we're looking at right now is the contour setup here. We can look at this stress here. We want to look at as the equivalent stress, and we can update that screen. We can see those results inside of here, and that this reduced quite a bit on the stress side of things. We can also change this over to our displacement magnitude and update that as well. And we can see it's still in the same displacement, but it's a lot less than what it was in the beginning. So we can change those variables to see those results, and again, you can animate it and see how different the model works based on where this brace has now been adjusted and modified based on its thickness, the width, and the location of that start along the X direction and the Z direction there. So this is a very simple example of the tool, but a very nice way to show how this can actually go through multiple iterations, because if you try to do this manually, it's going to take you quite a long time to do this, but it's a very handy tool. And there's also other capabilities inside of here. If you have a really complex geometry and you're only looking for certain areas, you can also localize this to look at select geometry elements and your peak or average values at those areas to really refine this down instead of looking at everything in the model. If you have a big model, you don't want to do everything, just maybe certain key critical areas, you can refine that. So this is just a quick example. So let's go ahead and close this. And what we're going to do is going to stop this, and we're going to hop over into our next example, which is the platform example, to show you another case of how this can be used. So let me go ahead and close this. We're not going to save anything, and then we'll go ahead and open up the next model. So again, this is our platform model that we saw in the design. So again, this one is very similar to the model that we just run. And I'm not going to run this all the way through here. I'm just going to kind of show you what we've got going on. So we've already added a load on the top of all these braces here, or these beams. So there's the load going down. I've also put another load on the side here, or normal pressure, to basically kind of push it in, to basically think if something's running into this, some other lateral load or that's going onto this, to see how this will adjust with this brace here. So this brace is mirrored on the other side, and we have parameters that drive how far it is from the top of this the green steel beam here, so it can move down for the values, and then we also change the angle of this to adjust the strength of that and rigidity of this platform. So that's what we want to know. And so we've already kind of, if we go down to our results here, you can kind of see what the default results are on this. If we turn this on, let's look for the magnitude, for example. Here, we'll go ahead and update the screen here. And this is kind of our magnitude for this, our default size here, and what we have for our parameters. If we look at this, I'm going to go back into here, look at our parameters. We basically really have these two parameters, but this case has a lot of parameters. There's like 300 something parameters in here, and I kind of show you what, how we handle this in the optimization tool. So in this case, we have our offset from the top, which is what I was explaining earlier, and then our brace angle. So what we want to do is to set this up. We don't really need to see some of these. When you look at the contours, for example, I'll go ahead and update this again. You can see that it's showing all this information here. We don't really need to see that when we run the analysis, so we can turn off those annotations if we don't want to see those during the analysis. It doesn't really help us any. And then on our add-ins, if we don't want to see these as well, we can turn those off as well. So we can just basically focus on the results and what our displacement magnitude is. So again, this is our animated scale, how it's moving right now with that load. So we can see that adjustment that's happening there. And so what we're going to do is we want to go ahead and run this optimization. So if we go into our optimization, we can see again, I've already got this saved once, so I'm not going to go through the process, but basically all those transferred parameters came in because they're not used in expression, so they're all there. So I basically just disabled all of them and just selected the top offset, enabled it, and then the brace and enabled it. So these are the two that I'm driving, and we can set up the initial value and the maximum value for this, and the brace angle. So I want the brace angle to start at 35 and maximum at 55. So, really we kind of have an idea of how this is going to, what values we want to use for this, but let's go ahead and run that optimization. And we're really looking for the displacement in this. We don't really care about the other ones, but we can add other data inside of here that we want to do for our targets. If we want to add a strain, for example, which wouldn't really be too much in this, but we could add that as if we wanted to see those values. But this is what we want to do for this particular thing. So what I'm going to do is go ahead and run this optimization and let it run. It takes about 6 minutes to run, so I'm going to speed it up a little bit, and then we'll come back to the results and show you what the optimization result came back with. So let's go ahead and go ahead and pause this for a second, and we'll let that run. Okay, and in this case, it came back with a offset of 10 and 55 with the maximum displacement, or sorry, the minimum displacement in this particular case. So we'll go ahead and OK, and we can apply yes to that result. It'll update our model, and now we can animate the scale just to see how that's going to be resulted here. And notice our displacement is about 12 compared to what we initially started out with. I think it was 20 something inside there. So this is basically giving us the minimized displacement in this particular case using that optimization module. And it went through, in this case, various iterations, 8 different iterations to get to our results for this case. So that's giving you an idea how we can use this model to get to our optimized designed parameters for our targeted results. So let's go ahead and hop back over to our presentation. Okay, in summary, so again, this is a powerful add-on to our multi-physics for IronCAD's basic or advanced modules. So you can, as long as you have IronCAD basic or advanced, you can add this module to it. And please speak with your local reseller to get some ideas on the pricing for this module. Again, it's used to drive IronCAD's design parameters to meet optimization targets that you set, and to basically return your optimal design parameters for that case. Again, you have multiple optimization methods that you can use to control it, to be more to meet basic needs or even more complex analysis. You can set multiple optimization targets and weight those to get the results based on what's important. It's fully integrated into IronCAD, as you saw, and it's through the MPIC integration that we have. And it utilizes multiple core processors for performance. So you can see that this is pretty quick. And that's basically due to the multiple cores, and also using the technology in multi-physics, which is our CFA technology and our auto-tying meshing capabilities, to allow you to mesh those assemblies really quick and do this analysis on a typical PC without having high-end rendering farms, things like that to do this. You can do this on your local PCs with these multi-core processors. So that's in a nutshell, that's this module for optimization for multi-physics. I hope you enjoyed this presentation today. And along the way, you can ask questions throughout the webinar, and we will respond to those in follow-up emails, or you can simply reach out to some of our resellers or your local reseller to get some additional answers and questions to this module. And we hope that you found this webinar useful today, and we look forward to you in our next one. Thank you.